Hey, welcome back to ECE 382. This is Module 16, and we are going to study how to measure speed of motors. Okay, so to measure motor speed, then we need to use Hall effect sensors. Okay, so these two small devices, these are Hall effect sensors, and this small disc is a 6-pole magnet. Okay, 6-pole means we have NS, 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 so we have 6 poles. Okay, so the Hall effect sensors basically just measure the magnitude of a magnetic field. Okay, I show you a movie here. Okay, so as the disk is rotating here, okay, and then these red things are small magnets, and then this the Hall effect sensor can detect the magnetic field, right? So that is Hall effect sensors. So basically, whenever we have a north pole and like this, north poles, and then we have a logic high, right? And then we have a south pole, then this guy, then we have a logic low, right? So when we have a fast rotation, okay, so distance between two edges is very close. When it rotates slowly, then the distance between the two edges here, so let me call this delta t, is larger, right? So again, this is a north pole. Okay, so with this delta t, we can find the speed, okay, speed of the motor, that then we can find the speed of the wheel. Okay, so then how about the direction of the motion, right? So basically we have two sensors, and then they are separated by about 90 degrees. Okay, so the as the magnet rotates, then as you can see here, that the N pole can go through S1 first, and then followed by the S2. So the pulses from S1 and S2, they look like this, and then there is a slight delay like this, right? So basically, in this case, we say S1 leads S2. Okay, in this case, we can tell it is a counterclockwise rotation, right? If the S2 leads S1, as you can see here, okay, so here the rising edge is here, and then rising edge of S1 is right there, and then so in this case S2 leads S1, okay, and then we can tell this is a counterclockwise rotation. Okay, so this is how we can tell the direction of the motion, or direction of the motor rotation, right? Okay, so so we have a motor inside this box here. Here is a motor. Okay, and then the magnet is connected to the motor, and we have a gearbox, and the gear ratio inside here, it is 1 to 120. That means that I'm sorry, when the wheel rotates one time, then motor rotates 120 times, right? So we have 3 N poles, okay, here. So we have 120 turns and 3 N poles, north poles. That means we have 360 pulses per the wheel revolution, right? So every time the wheel rotates one time, then there should be 360 the pulses from these two the Hall effect sensors, right? So we have 360 pulses, okay? And then the diameter of the wheel is a 70 millimeters. So the circumference of the wheel is pi d, which is a pi times 70 millimeters. Then this is about 220 millimeters, right? Right, so the wheel makes one revolution, okay? This wheel makes one revolution, right? And then the motor makes 120 revolutions. Then we have 3 north poles, so that gives us 360 pulses, okay? That is equivalent to 220 millimeter wheel displacement, okay? So that means also that the one tachometer pulse, that means this one pulse, okay, that means 1 degree rotation of the wheel, right? Okay, so we want to measure the time between pulses, right? So this is the pulses from tachometer, okay? And then here's a rising edge, and here's another rising edge, right? So we want to measure between rising edges. So let me call this delta T tacho, okay, tach. So we want to measure this the time between two rising edges. Then we want to use a timer, okay? So basically, you know, between this, then we want to measure the number of pulses of the timer, right? And then let me call the period of the pulse, I mean the timer, okay? Let me call this TC of TA3, right? Okay, so we have 1 tachometer pulse, okay? That means 1 degree of rotation of the wheel, okay? For each 1 degree rotation or each tachometer pulse, then we have n timer pulses, okay? So here is 1, 2, 3, and then up to n timer pulses. Okay, so we can count the number of timer pulses, okay, between rising edges of tachometer. Okay, so let's choose the SM clock, which is 12 megahertz, and a prescale of 1. Then the TA3 clock period will be 1 over FCTA3, which is 12 megahertz, and then the period, the clock period of timer 3 is going to be 83.333 nanoseconds. Okay, and then let n be the number of timer pulses. Okay, so these are, you know, these timer pulses. Okay, so that is a number of pulses here is n. Okay, and then or the number of timer pulses, or n, the value of the value of n is basically stored in TA3 CCR0. Okay, we're gonna revisit this one in a few minutes. Okay, then the angular speed of the wheel is given by this equation here. So let me just bring up here a little bit. Okay, so the one pulse is basically this one pulse here. Okay, TC-TA3, it is 83.333 nanoseconds, right? So 83.33 times 10 to the negative 9th seconds, okay? And 1 degree of that corresponds to n pulses, okay? So this 1 tachometer pulse, that is 1 degree rotation, that corresponds to 1 timer pulses. So 1 degree is n pulses, and 1 revolution is 360 degrees, okay? And then 60 seconds is 1 minute. Then if you do this simple math, then you're gonna get approximately 2 million, okay, over n RPM. Okay, so this is the wheel speed. So again, the value of this n, you can get it from TA3CCR0, right? And then you can just simply just plug this value into this equation. Then you can find the wheel velocity. Okay. Next slide. Okay, so the largest value stored in TA3CCR0 is 2 to the 16 because this register is a 16-bit register, right? So the slowest speed we can measure is, so omega will mean the minimum speed that you can measure is a 2 to the 16th. Okay, that is about 30 RPM. Okay, that is slowest speed you can measure. Okay, so there are 2 different modes in timers. So the first one is output compare mode. So this is what we use in modules 13, 14, and 15 for PWM, okay, bump sensor ADC, and timer A1. Okay, so second mode is input capture mode. Okay, to explain the difference between the two, then let me just go to Google timer. Okay, so there are 2 different modes. Here, one is a timer and the other one is a stopwatch. Okay, so timer is basically you set a fixed time and then you start. Then in 5 seconds, then it'll beep. Or this is an interrupt, right? So every 5 seconds, then we're gonna do something. For example, use a task. In the stopwatch mode, then you start, and then it just it runs, right? And then until you hit stop, and then it tells us, you know, the time elapsed, right? So let's go back to the slide. So the timer, the Google timer, that is basically output compare mode. Okay, so the examples are you know, every 10 seconds and do something. For example, the ADC, read ADC values or check bump sensor, okay, or read IR distance sensor. Okay, stopwatch mode, this is input capture. Okay, so it tells us how long it takes. For example, the time between tachometer rising edges. Okay, so these 2 are main differences. And so there are compare and capture mode. In this module, we're going to use capture mode. That is capture mode, right? So in this module, then we're going to use capture mode, right? Okay, let's look at this register. The first register we need to look at is timer A3 CTL. Okay, in your code, it is timer A3 arrow CTL. Okay. Also, you can look at you can find this table in this file section section 19.3. Okay. So first, we need to choose SM clock. Okay. So that gives us 12 megahertz, and the input divider is going to be just divided by 1. Okay. So then 12 megahertz divided by 1, that gives us 12 megahertz, right? And at the beginning, we need to hold the timer. Okay, so that's at the beginning, we need to hold the timer. Okay, once everything is ready, then we need to set it to continuous mode, right? And then we need to clear the timer, right? So these two, you need to make sure that you just set 1, 0, for continuous mode, and you need to clear the timer. So when everything is ready, right? And you also, in this case, you need to disable interrupt. Okay, so you disable interrupt for CTL, but later you need to you have to enable the interrupt for the next register. I mean CCTL. Okay, this register here. Okay, how about the EX register? Okay, so in your code it is going to be EX0. Okay, so because we're gonna use pre-scale of 1, you need to use divide by 1. Okay, so that's what we want to use. Then the clock frequency of timer A3 is going to be 12 megahertz divided by 1, times 1, which is 12 megahertz. Okay, and TC TA3, which is timer A3 clock period, that is 1 over 12 megahertz, which is 83.333 nanoseconds. Okay, that's where we got this number in the previous slides. Right, and then the next register is a CCTL. Okay, so we have as you remember, I hope, that we have a CCTL0 to CCTL6. Okay, so we have 6 CCTL registers. Okay, we use 2 registers, 2 CCTL registers. One of them is a CCTL0, and another one is a CCTL1. Okay, so CCTL0 is for your right wheel, and CCTL1 is for your left wheel. Okay, so the previously, like when we used the output compare mode, we had no capture, right? But now we need to use a capture mode, right? So we need to have a capture on rising edge, okay? Right, because we need to measure time between the rising edges of a tachometer, right? Then we need to have CCI mode, okay? And then synchronous capture, right? And then capture mode, yeah, and then should be capture mode, right? Okay, and then so this one is we don't care. So this is the compare mode, right? And then here we need to enable the interrupt. Okay, we need to enable interrupt of a CCTL0 and CCTL1, and we don't need this, we don't need this, and we don't need this, right? And then we need to clear the interrupt pending. Okay, so that clears interrupt pending. Okay, and then this is a very important because you need to clear this bit every time IRQ handler is called, right? Okay. Right, and then CCR register. So we have two registers. So one is CCR0, that is for the right wheel, and CCR1 is for your left wheel. Okay, so basically you want to read this these two registers to get the number of pulses, right? So we need to read CCR0 every time IRQ handler is called, right? And then let's CCR0 is 50,000, okay? And then so we're gonna use the velocity equation that we discussed a few slides ago. So that is a 2 million over n. So n in this case is 50,000, okay? So that gives us 40 RPM. Okay, so this is how you calculate the speed of the wheels. Okay. Okay, so the IO pins, right? So 10 port 10.5 and 10.4, those are the timers. Okay, so basically that gives us a number of pulses from tachometer, right? And then 5.2 and 5.0. Okay, so 5.2 and 5.0, this is a GPIO. Okay, and then that gives us the wheel direction. Okay, so when the pin is high, the input is high, that means it is moving forward. Okay, if it is low, then the wheel is moving backward. Okay, so that's how we can tell the direction of the wheel, right? And 10.4 and 10.5, those are for timers. Okay, so you know to use, so this is not GPIO. Okay, so we have to let the timer control these two pins. Okay, so then we need to use a secondary function mode, right? So as you probably remember from previous sections, so if you set cell selection register, cell 0 register, and cell 1 register, if you get 0, 0, that is a GPIO mode. Okay. If you put primary mode, then you're gonna put 0, 1 for cell 0 and cell 1 respectively. And if cell 0 is 1, cell 1 is 0, that is secondary mode, right? So last one is 1, 1. So you use this one for ADC. Okay. Right. And how about the interrupt? Okay. So TA3. Okay. So the interrupt the request number IRQ, that is a 14 and 15. Okay. So we need to look at these two numbers, right? So that then we're gonna call these two functions, right? Okay, so okay, so you can also find these tables in SLAU 365h.pdf or i.pdf. Okay, so I just got it from page 116. Okay, so you need to look at ISER0. In your case, in the code is going to be NVIC ISER0. Okay, since the IRQ interrupt request number, they are 14 and 15. Okay, so we have to set these to 1. Okay, and then the IRQ, interrupt are enabled, right? The CPU can handle the interrupt properly. Okay, and the next thing is we need to set the interrupt priority. Okay, so the IPR3 register, we have a PRI 14, okay, and PRI 15. So we need to set these field, and because this is IRP3, then in your code it's going to be NVIC IP3. Okay, and then the bit 31 to 29, and also 23 to 21, that you need to have priority of 2. Okay, that's you need to set. Okay, that's pretty much it. And then I also want to discuss a little bit about sensor noise. Okay, so the actual signal we're gonna get is some, so I'm sorry, this is ideally, okay, so we have really nice sinusoidal signal as this disc is rotating, right? And then there is a threshold. So if the voltage is greater than this threshold, then we consider that as high, otherwise low, right? It goes like this. So we have very nice pulse, okay, or pulses like this, okay. So this is really ideal case, right? But actually, that's not what we have. Okay, so we have some kind of very noisy signal coming in like this. It's not, this kind of a nice sinusoidal signal. Okay, so the actual voltage coming from the Hall effect sensor, may look like this. Okay, and then we have a threshold. That what we really get, in your board, or like a digital signal, is going to be something like this. Okay, here is a threshold, here is another threshold, this is high, okay, and then here that is high, okay, and then low, and then high. Oh my god, here is crazy one, okay, and then like this, right? So in your board, they may read this small period, okay, and you can see the delta t is very small, okay, because delta t is very small. Then it will ends up give you extremely high speed of the wheel. Okay, so these are basically like glitches, and then we cannot really avoid this kind of stuff. Okay, so in your final project, that you may want to implement a software debouncer. Okay, so we're gonna talk a little bit more about this debouncer later, but you should expect this kind of effect for your for this module 16. Okay, so you may have sometimes a really extremely high speed. It's just because of this kind of noisy signal coming from the Hall effect sensor. Okay, that's all I have, and have fun with your lab.